9a Thermal Energy. 9.1 Introduction. The sun's going forth is from the end of the heaven, and his circuit unto the ends of it, and there is nothing hid from the heat thereof. Psalm 19:6. The sun is one of the most glorious of all God's creations. Humans have always marveled at its beauty and power. In ancient times, most people worshiped the sun, but the Bible teaches that the sun, glorious as it is no God. It exists not to be worshipped, but to serve the purpose of its maker. The Bible indicates that God's purpose for the sun is to benefit mankind. We were not made for the sun. The sun was made for us. Genesis 1:16-18. Deuteronomy 4:19. As we use the sun's energy, we fulfill our God-given purpose to exercise good and wise dominion. Genesis 1:26-28. Since God made the sun so that nothing could be hidden from its heat, we should learn how best to use this vast source of clean, renewable energy. But what is heat? How is it produced? How do we measure it? How do we use it? Is it possible that the sun could be a reliable, inexhaustible source of energy to solve our dominion science problem? 9.2 Early Theories of Heat. In the 6th century BC, the Greek philosopher Heraclitus claimed that there were three natural elements: earth, water, and fire. His writings greatly influenced later philosophers, such as Socrates and Plato. Because of the philosophical ideas of these men, people believed that heat and fire were the same for many centuries. In the 13th century AD, many philosophers and scientists suggested that motion is the essence of heat, such as when you rub your hands together to produce warmth. This concept was reaffirmed around 1600 by the famous English philosopher and scientist Francis Bacon. In the early 1700s, Daniel Bernoulli suggested in his theories of fluid flow that matter was made of particles. His theories also stated that while gas pressure was the force of these particles colliding with matter, heat was their kinetic energy transferred to matter. It was difficult for scientists to accept this theory because most of them had not accepted a particle model of matter, which was its basis. Later in the 18th century, Joseph Black suggested that heat was like an invisible fluid. Solids needed to be filled up with this heat fluid until they melted. The great French chemist Lavoisier further developed this idea and called the heat fluid caloric. The caloric theory of heat was quite successful in explaining observations and making predictions. Lavoisier considered caloric to be an actual fluid, so the matter in caloric could be neither created nor destroyed, according to his law of conservation of matter. Caloric was thought to consist of self-repelling particles that adhered to matter. This theory explained why heat flowed from hot to cold. Hot objects had a lot of caloric, while cold objects had little. Calorie naturally flowed by self-repulsion from areas of higher concentration to areas of lower concentration. Temperature was a measure of the density of the caloric fluid, the amount of caloric per unit volume. Nearly all the gas laws could be explained by the caloric theory. For example, when air molecules absorb caloric, they become warmer because of a greater concentration of caloric. They also grow in size as the caloric particles attach themselves to the air particles and occupy a greater volume, explaining Charles's law. Both physical and chemical processes could release or strip particles of their caloric, raising the temperature of their surroundings. The most significant successes of the caloric theory involved the development of a scientific theory of steam engines in the early 1800s by Nicholas Sadi Carnot. See the facet on page 181. He explained the process by which these engines work, using only the caloric theory. In addition, the theory allowed significant progress in understanding how gases expand according to Newton's laws, and in determining the speed of sound in air. Carnot's work evolved into the science of modern thermodynamics, which is the study of thermal energy and heat, and how they relate to other kinds of energy and work. 9.3 The Kinetic Molecular Theory of Heat. The first serious blow to the caloric theory was dealt by Benjamin Thompson, who lived in the 17th and 18th centuries. Born in the Massachusetts colony, he was an interesting combination of spy, traitor, statesman, soldier, nobleman, and scientist. In 1797, he was the director of the Munich arsenal in Bavaria. He was known then as Count Rumford. During military raining maneuvers, Rumford observed that cannons fired without cannonballs became much hotter than those that were fired normally. If the caloric theory were true, the release of caloric and the resulting temperature rise should have been unaffected by the presence of the cannonball when the gunpowder was fired. Later, in his role as director of the arsenal, one of his duties was to supervise the manufacturing of weapons. This allowed Count Rumford an opportunity to observe cannon boring operations. The cannon boring procedure was relatively simple. A solid metal cannon casting was mounted on a rotating shaft turned by horsepower. A cutter pressed against the end of the cannon drilled out the bore as the barrel rotated. As the boring progressed, great quantities of heat were released enough, in fact, to boil the water that was poured into the barrel to cool the cutting tool. How was this heat produced? According to the caloric theory, the metal chips removed by the drill released their caloric. As more metal was removed, more caloric should have been set free. Rumford noticed, however, that the duller the cutter, the greater the amount of heat produced, even though less metal was cut away. This finding contradicted the caloric theory. Rumford devised an experiment in which he encased the cannon in water while it was being drilled. He used a dull bit and measured how much water could be boiled during the drilling process. He calculated that drilling released more caloric than should have been needed to melt the entire cannon. By repeating this experiment again and again with the same cannon, he showed that the caloric supply seemed inexhaustible. Clearly, the caloric theory was unable to explain these observations. Rumford concluded that motion was in some way responsible for heat, but he was unable to provide a clear cause and effect explanation. Julius Robert Mayer was the first to experiment with the idea of heat as energy, not as matter, in 1842. He used a horse-powered mechanism to stir a large pot of paper pulp, calculating the mechanical energy needed to heat the mixture. His finding demonstrated that mechanical energy could be converted to thermal energy. This conclusion was largely ignored by physicists because Mayer was a medical doctor and his experimental procedure was fairly crude. It was not until many years later that he was finally given credit for his discovery. James Prescott Joule is usually recognized for first showing a clear connection between mechanical energy and heat. He performed experiments using all sorts of mechanical devices that were dropped, shaken, and stirred to produce changes in temperatures of liquids and gases. He concluded that the equivalent of 4.18 Newton meters of mechanical work would raise the temperature of 1 gram of water 1 degree Celsius. This finding clearly established that the cause of a temperature change in matter was not a material fluid, but a form of energy. He later worked with William Thomson, Lord Kelvin, to calculate the speed of molecules in air based on their kinetic energies, helping to firmly establish the kinetic molecular model of thermal energy. See subsection 6.6 on page 114. 9.4 The nature of thermal energy. According to the kinetic molecular model, atoms, molecules, ions, and their subatomic particles are in constant motion and thus have kinetic energy. In addition, they exert attractive or repulsive forces on each other that generate potential energies among the particles. The sum of all these energies is called the internal energy of matter. This energy cannot be measured. Internal energy can be affected by changes in a system's pressure and volume, as well as by the exchanges of thermal energy with its surroundings. The thermal energy of that system is the average sum of the kinetic energies of its particles. Thermal energy is thus part of the system's internal energy, but it is not the same thing as internal energy. While thermal energy content cannot be measured directly, changes in a system's thermal energy can be measured. When a warm object is brought into contact with a cooler object, the higher kinetic energies of the molecules of the warmer object are transferred by collisions to the molecules of the cooler object, which have lower kinetic energies. The transfer of particle kinetic energy is called heating or cooling, depending on the direction of thermal energy transfer. A loss of thermal energy is usually indicated by falling temperatures. A gain of thermal energy is usually accompanied by rising temperatures. You will learn more about the transfer of thermal energy in Section 9C. 9.5. Using solar energy to solve problems. The work of Joule, Mayer, Watt, Carnot, and many other scientists in thermodynamics is key to solving our Dominion science problem. For a renewable energy source to be valuable, we must be able to convert its energy into a usable form. Can you think of a way to change the sun's energy safely and economically into electricity? How can the sun's energy be concentrated? Does the technology exist to do this? Solar panels, properly called photovoltaic or PV panels, can change sunlight directly to electricity. The earliest PV panels were very expensive and inefficient. Though modern PV panels are more economical, they are still costly compared to other forms of energy. Even so, there are many PV electricity generation facilities being built around the world where sunlight is plentiful. These facilities produce safe, renewable energy from the sun. Energy costs continue to rise, and these costs erode the wealth that a nation needs to build a financially sound society. Is there a more economical way of converting the free energy of the sun into electricity? One emerging technology is the solar thermal, ST, power plant. ST power facilities use large arrays of steerable mirrors that reflect sunlight to heat water or other kinds of fluids. Eventually, hot, high-pressure steam is produced, turning turbine generators to produce electricity. The largest ST power station in the world is the Solar Energy Generating Systems facility, located in the Mojave Desert in California. Its installed generating capacity is 354 megawatts, MW of electricity. At night, when solar energy is not available, it uses natural gas to run gas turbine generators. This permits the plant to generate electricity all day and night. Dependence on daylight hours is a major weakness of solar energy sources. Some ST plants are experimenting with storing superheated water for generating steam during periods of darkness and cloudiness. Right now, some plants can store heated water for about an hour, but new approaches to this problem are being investigated. Solutions may include storing thermal energy in liquid sodium reservoirs, or using the latent heat properties of phase changes in other materials. See Section 9C for a discussion of latent heat.